Hello my esteemed viewers. In this tutorial, we will make a foray into machine learning. That is, we will be barging into machine learning from the fundamental steps or from building blocks of machine learning. As you would have guessed, we start with definition of machine learning. Actually, in the literature, the definition of machine learning is huge in number. Okay, there are multitudes of definitions available for machine learning, connoting different phases of this machine learning. That means machine learning definitions galore. Definition 1 says that machine learning is all about turning data into information. Simply put, machine learning allows the user to feed a computer algorithm an immense amount of data or huge data, copious data, and have the computer analyze and make data-driven recommendations and decisions based on only the input data. This is the meaning of this particular definition. Definition 2 states machine learning is all about to make sense out of data. Machine learning algorithms works in a different way than the human brain. They create an image of reality that is not always understandable for our minds. That is the meaning of this. And you give the data in terms of its coordinates, in terms of its features, it will come out with something which is not nonsensical. Definition 3 says making machine learning is all about making machine to develop programs or algorithms for tasks for which we do not have an algorithm. There are at least 9 examples to illustrate the veracity of this particular definition. Identification of spams, recommending products, and customer segmentation, image and video recognition, identifying or recognizing or detecting fraudulent transactions, and demand forecasting, virtual personal assistant, the sentiment analysis, and customer service automation. All these problems have been solved using huge amount of data, and all these problems do not come with a tailor-made algorithm. That is a definition. So machine learning could do the magic of solving these problems, and 9 problems have a place of sanctity in machine learning circles. Definition 4 says machine learning is processing volumes of data and developing a computer learnable model. As we see here, as the amount of data increases, the performance of the most of the learning algorithms have a bound for performance, while deep learning models, which are the higher echelons of machine learning, show high performance, maybe in terms of accuracy, maybe in terms of speed, maybe in terms of identifying differences, depending on the context. Definition 5 actually says, it should be 5, it's a branch of AI which concerns the construction and study of systems that can learn from data. Of course, machine learning is basically a method of data analysis that automates, that mechanizes, of course, building of a mathematical or analytical model without programming, of course. Such models can learn from the data for themselves, identify the patterns, and make decisions with minimal human intervention. Here, in this example, the apples and melons are mixed, and there is an unsupervised learning algorithms which will find the similarities between the items, and it will be able to categorize that into two items. Apples are apples and melons are melons. According to Tom Mitchell, called the father of modern day machine learning, here is a classical definition, or some kind of an academic definition of machine learning. A computer machine learning, or a computer or a machine is said to learn from experience E with respect to some class of tasks T and performance measure P. If its performance at tasks T as measured by P improves with the experience E. We repeat this definition to go a little deeper into the definition, and this is a mathematical definition of machine learning, as you might have guessed, my dear viewers. A computer or a machine is said to learn from experience E with respect to some class of tasks T and performance measure P. There is a performance measure for the task T. Of course, this task T is done using the experience E. Here experience E is nothing but the data or the features. If its performance at tasks T as measured by P improves with experience E, as the data deluge in huge volume, the performance measure goes on reaching its higher values, maybe in terms of accuracy, maybe in terms of prediction, or whatever. In order that, and here experience E means it could be data, it could be attributes, or it could be features or characteristic features. Here tasks means it could be prediction, it could be classification, grouping, guessing, identification, interpretation, decision making, etc., etc. And P is the performance measure. P is the minimum error principle, classification accuracy, principle of least squares, testing of hypothesis, p-value testing, and maximum entropy, etc. And these are all the performance measures. Of course, having said all these things, machine learning is not a panacea for solving all kind of problems, and this should be understood very thoroughly. That means, in simple terms, and if you have an algorithm for a problem, write the program, that's all. For example, sorting the names using bubble sort. We have bubble sort as an algorithm. Apply bubble sort and sort the names. And if it is a maze problem, we will just press depth first search into service, and we will solve this. We will convert this maze into a graph, and we will apply DFS, and we know where the turns and twists are and how to reach the destiny or destination. Therefore, a machine learnable problem or the concept will not have a tailor-made algorithm, right? And we can quote several examples. Of course, in order that the machine solves a problem, the problem should be well posed. I repeat, in order that machine learning is applicable for a problem, the problem should be basically well posed. That means we need to find what the definition of well posedness, or what exactly we mean by categorizing a problem as well posed. A problem is well posed if the following three properties hold good. It should be existent. Okay, the problem is really in existence. For all suitable data, a solution also exists. Uniqueness. For all suitable data, the solution is unique. Stability. The solution depends continuously on the data. As the data comes in huge numbers, temporal, which is time dependent, then also the solution should be available. That means if we simplify this particular well posedness or the definition of well posed problem, a well posed problem will have a solution in existence, and the solution is unique, and the solution is stable. And we can quote several examples for this. Checkers problem, and all these problems have been solved using machine learning techniques. Checkers problem, that is chess playing problem, handwriting recognition problem, signature identification, robot driving learning problem, robot navigation problem, leaf identification problem, disease identification problem, thumb impression recognition, gesture recognition, face recognition, emotion recognition problem, and the list is very big. Do we have readily available algorithms for all these things? No. Yet the solution exists for each and every problem, and the solution is unique for each and every problem, and the solution is stable, because as and when the data comes into the deluge, or the new data comes, the solution still exists. Okay, and we will find some kind of a general solution and also unique solutions. And it should be remembered, or it should be noted, that all these problems do not have a readily made algorithm. The just opposite of a well-posed problem is ill-posed problem, as you might have guessed. For the sake of completeness, we will quote some examples for these ill-posed problems. Ill-posed problems cannot be solved by a machine learning algorithm. A problem that violates the properties of well-posed problem is a ill-posed problem. A substantially complex phenomenon, a problem such that the probability of error is very high, we usually arrive at an unstable solution. That means ill-posed problems of this nature, which will have high complexity, which will have high probability of error. Okay, that problem falls under ill-posed problem category. And to quote the examples, differentiation is an ill-posed problem. Image deblurring, because we will not get the true picture if we deblur it after blurring an image. Inverse diffusion, predicting floods, temporal searching, mind reading, deducing temperature distribution from the final data, all these stand as examples for ill-posed problems. To simplify the definition of ill-posed problems further, ill-posed problem could mean a number of things. It could be that your problem is completely nonsensical, using undefined terms that make nonsense. That means, to quote a very simple example, a mathematical object that form an empty set. So the definition of empty set, no objects in existence. But we are trying to answer a question to find a set which contains mathematical objects, but still it is empty. And it could be a set of we are trying to find a set of all numbers that are both odd as well as even, and also the prime. And an ill-posed problem could be to asking a question to derive a statement from a set of contradictory axioms. Is square root of any number always positive? This is a contradictory statement and contradictory problem. You could also be looking at an ill-formed expression, like asking what is the truth value of a proposition with unbound logical variable. That means applying a function to a value outside its domain, like sine inverse of 2. Sine inverse of 2 doesn't have any, for 2 being a real number, doesn't have any solution. So my dear friends, in this tutorial we just explained as to what machine learning is, and we just quoted examples for each and every definitions. Okay, in machine learning circles we can find at least half a dozen of significant definitions or meaningful definitions of machine learning. We also saw a machine learning definition offered by the father of machine learning, Tom Mitchell, to be a little kind of mathematical in nature, but this is the definition which should be realized whenever we build a machine learning model. With this we will close this tutorial number 3, and if you are liked and if you are still not subscribed to my channel, kindly do that. Until then, bye.